Imagine for a moment standing on the threshold of an impossible journey. Not a trip across town or even across continents, but across the unimaginable cosmic gulfs that separate stars and galaxies. Picture a doorway, not of wood or stone, but woven from the very fabric of space and time. You step through, and in an instant, the light of a distant alien sun bathes your face. You've just traversed light years in a heartbeat. This isn't just a fanciful dream from the pages of science fiction. It's the profound, mind-bending promise of traversable wormholes, theoretical shortcuts through the universe that could reshape our understanding of travel, distance, and even reality itself. Our journey into this extraordinary concept truly begins with Albert Einstein. Back in 1910, he started to unravel some revolutionary ideas about space and time, concepts that would forever alter our perception of the cosmos. But it was in 1915, with the advent of his groundbreaking theory of general relativity, that the true revolution began. Einstein didn't just expand on space and time, he masterfully wove gravity into the cosmic tapestry, revealing it not as a mysterious force, but as a direct consequence of massive objects literally warping and curving the very fabric of space-time around them. Think of a bowling ball placed on a stretched rubber sheet. It creates a dip, and marbles rolling nearby will curve towards it. That's space-time curving around a planet or a star. Within the intricate equations of general relativity, a curious possibility emerged: wormholes. These aren't just theoretical constructs, they are described as curved regions of spacetime that act like cosmic tunnels, connecting two incredibly distant points in the universe. Picture two far-flung cities on a map. A wormhole would be like folding that map so the cities touch, creating a direct passage that bypasses the long, winding road between them. It's a shortcut, a cosmic bridge from one side of the universe to another. Yet, despite their elegant theoretical existence, we must pause and acknowledge a crucial truth. Scientists have never directly observed a wormhole in nature. There's no empirical proof of their existence to confirm the theory. And even if they did exist, the general consensus among scientists has always been that any such wormhole would be extraordinarily unstable. Imagine trying to step into that cosmic tunnel. The moment you began your journey, the immense gravitational forces within would likely cause the tunnel to collapse almost instantaneously. Your journey would be cut short. The matter attempting to pass through would be severed, disappearing, perhaps trapped forever in whatever remote corner of space the wormhole once briefly led to. It's a beautifully elegant concept, but one seemingly fraught with insurmountable peril. But here's where the story takes a fascinating turn, where human ingenuity and theoretical physics push beyond the perceived limits. What if there was a way to defy this instability? What if we could keep these space-time tunnels open, stable enough for something or even someone to pass through? Some visionary scientists have theorized exactly that. One compelling idea involves the use of what's called negative mass, or more accessibly, exotic matter, like specific configurations of electrons. The premise is that this hypothetical negative mass could generate an anti-gravitational effect, essentially counteracting the electric charge and immense mass of the wormhole itself, preventing it from collapsing inward. It's like using a tiny, incredibly powerful invisible spring to hold the tunnel open. Another ingenious theory proposes a different approach, one that sounds almost simpler in its elegance. This theory suggests that by layering the wormhole entrance, perhaps the mouth of the tunnel, with shells of regular conventional matter, the tunnel could be stabilized. Think of it like reinforcing a fragile natural cave with structural supports. These shells would provide the necessary outward pressure or stabilization to keep the portal from pinching shut, allowing matter to pass through safely. These aren't just abstract musings. The researchers who've proposed these discoveries are actively planning to test these theories experimentally. While these experiments would likely not involve building a life-sized wormhole in a lab anytime soon, they could involve simulating the exotic conditions or material properties required, pushing the boundaries of our current understanding of quantum mechanics and general relativity. If, and it's a colossal if, these theories prove true, the implications are breathtaking. Our greatest science fiction dreams of instant interstellar travel, of traversing light years in moments, perhaps even of a regulated form of time travel, could move from fantasy to scientific possibility. It would fundamentally challenge our understanding of the universe, of what is possible, and of our own place within this vast, incredible cosmos. It would mean that distance is no longer an insurmountable barrier, that the vast emptiness between stars might just be a fold in a larger fabric, waiting to be traversed. So, as we contemplate these stable wormholes, these theoretical conduits that could reshape space, time, and reality, we're not just discussing physics. We're discussing the very essence of human exploration, our eternal quest to understand the universe and unlock its deepest secrets. The journey to truly comprehend and perhaps one day harness these cosmic shortcuts is just beginning. What are your thoughts on the possibility of stable wormholes? Do you believe humanity will ever achieve such a feat? Share your ideas in the comments below, and let's continue this fascinating conversation about the future of space, time, and our place within it.